Okay, good evening, everyone. Today is the final session of our long 4 5 month long course with ranging over 50 60 hours. We covered a lot of topics, but today we'll be having the final session, final class, where we'll be talking about one class of models called mixture models and one specific type of algorithm used to train them known as expectation maximization algorithm. This would also give you a grounding or a background to understand advanced models like VAEs as you go ahead and study more in these topics. So please forgive my bad voice. I'm having a bit of a fever. So let's start. So till today, we have discussed majorly three different parts or four different parts of our on this course regarding probabilities, linear algebra, unsupervised learning, supervised learning, and finally we are going to learn about something known as generative modeling. Is what we'll be doing today. We'll have a glimpse of what is a generative model. Uh, so please follow. So all this while, do you agree? What we were trying to do is we were trying to model py given x. That is, we were trying to say what is the probability of a label, being in a class C given a data point. So what is the probability of a data point? Sorry, data point being in a class C. So the data point is given to you. So the data point was given to you, so you were finding out the conditional probability of the data point. So these are called discriminative models, as the name may suggest. They used to discriminate between different classes or discriminate between categories of objects. Discriminate regression can also be thought as a discrimination problem because you're actually predicting y from x. On the other hand, generative model is much more general. Generative model is trying to learn the actual distribution of the data. So instead of learning P of just learning a label of function from X to Y, what it tries to do is it tries to learn a function, learn the entire distribution itself. So say your underlying distribution was this. Say in discriminative models, say these were your two distributions, class 0 and class 1. You'll do this in your assignment as well. You'll understand that better. Then, according to our discriminant functions and Bayesian probability, this would be our decision boundary, right? Something like this. Right? This would minimize the error. Do you agree? This would give me y given x. So given a data point x, this will predict class 1. This will predict here class 0. Right? But in real life, you do not know the distribution of the data. Moreover, what you try to do is you have samples of these data points. And what you try to do is, in generative models, you try not to learn the decision boundary itself, but you try to learn these distributions themselves. Why not? Learn the distribution itself. Instead of the decision boundary. Is the motivation clear? Any questions? Okay. So you try to learn, say you have one normal mu1, sigma1, you try to learn these distribution itself. So what is the use of these learning these distributions? Can you tell me? There are two uses. One is once you know the distribution, say you know y equal to say y class equal to 1, you know the probability distribution of x. then you can sample from the distribution, right? That's what we see in DALI 2 or any generative AI that we see around the internet today, right? Once we know the distribution, we can just sample from it. That will be output of the distribution. If we know the distribution of faces, we could be able to sample the faces from the distribution. If we know distribution of text messages or Shakespearean English, we could only sample from that, right?
Yes.
So if we know the distribution, we have much more information compared to discriminative models, right? So you see, once you know the distribution, you can also do discrimination because you can find out the posterior, right? It's simple. P of y given x is P of x given y into P of y by P of x. So this is your generative model. So if labels are there in the data set, P of y given x is a generative model. If labels are important, you can have simply P of x as your generative model if there is no labels, if no labels exist. So we will only be looking at this version today. There are ways to incorporate labels into generative models. We'll not go into those. They're much more advanced topics. But the idea is you can also incorporate labels into generative models. Like you can tell your model, make a girl's face versus make a boy's face, make a face with beard, or make a face with maybe some blush, something like that. But we'll be here today. We'll be trying to learn. We have only we have only the data space X, and we do not have labels according to them. So now let us, having understood the intuition of this problem and the large motivation, let us get into the formulation. How do you try to learn this? So this is very special class of algorithm or models called mixture models. Generally, if I tell you that there is a data, can you give me one algorithm yourself? Well, let us warm up. I tell you that data, I'll not even tell you this. I tell you something like this. I give you this data. Right? This is the height of students in the class. This is probability, right? So what would you use to model this data? So your data is given to you. So if you want to sample a height of a student, how will you first learn the distribution? What would you do? What would be your easiest choice to take? So if I give you this data, this histogram.
Like by looking here, we can say it is a normal distribution.
So we have seen by central limit theorem, all distribution converges to the normal, right?
Yes.
So we can assume that if it's a single distribution, if it has enough data points, it will be a normal distribution. So we can say that the mu of the distribution by law of large numbers will be the average height 1 by n, height 1 for I equal to 1 to n, right? Correct?
Yes.
And we can say sigma squared will be 1 by n, again sample mean, sample variance, height I minus mu whole square. So now you know that height is sampled from this normal mu sigma squared distribution. Now if you can just sample from this distribution, you will get a new height, and you will see that that height would be fitting in that class without people doubting. Right? But in reality, you do not have a single distribution, or you don't even hit. This is also one dimensional. You will have multi-dimensional sync of faces, right? Faces would be like 256 cross 256 cross 3 is your dimension. And your faces can be various types. So your face can be a girl's face or a boy's face, an Indian face versus a Chinese face or an American face or an African face, right? So as we were thinking, they could be different clusters of the data, right? But in more versatile data, or data with large range or variation. Do you agree there would be clusters like these? So this can be African, Indian, European, and so on, right? So a single Gaussian would not be good enough. Is the motivation clear? I hope. So in this case, what would your solution be? But I know that these faces, whatever European face, Indian face, African face, they themselves are normal distributions. Then what will I do? I will assign different normal distributions to all of them and sort of have a mixture of all of these or an ensemble of all of these normals. Is the idea motivation clear? Any questions?
Like you are telling each individual cluster is a normal.
That's what exactly will happen, right? So you think if there is so much variation amongst the faces, each of them you cannot represent by a single normal. That's the idea. Think of
Yes.
think of Indian height and American height. They would be different distributions. You cannot model them by a single normal, right?
Yes.
So that's the idea. So if you had modeled by a single normal, you would have got a very bad fit. So this is the idea. So if you think of height, say you have, this is India, this is Japan, this is European, this is Jamaican, and so on. Right. So you will see that you need multiple Gaussians. But now what is the problem? Can you tell me? How do I assign Gaussian to each of these, right? There's a conflict, right? Once you know that there are multiple Gaussians, you will have to assign one Gaussian to one data point. Like you have to learn each of the Gaussian for each of the sub distributions that you have. So the idea is in the worst, yes. So in the worst case, this model will always work because say you have infinite Gaussians, then you can learn one Gaussian per data point, right? Why GMM always works? Why GMM theoretically has to work? Because if you have infinite Gaussians, you can have one Gaussian per data point. Then each Gaussian, a single data point per Gaussian means one delta Dirac function, right? Normal, mu, zeros, no standard deviation. At mu, you have a singularity of the density, right? So like this, you can model the entire train of the data if you have infinite Gaussian. So the idea is you can have, therefore GMM can model any distribution provided you have infinite Gaussian. This is one you must keep in mind. It's better to have it out of the way first only. But you cannot have infinite of them. We'll have to see how can we, if we had infinite, we could assign one data point to each normal and just say that data point itself was the mu and there was no standard deviation. But now that doesn't make any sense. Then you are saying that each data point is a cluster, and that's a trivial solution, right? And you're not going to give any interesting sampling or predictions from that. Is that clear? We'll see both of this sampling and predictions today in a code. And once we have understood the entire GMM. So maybe not sampling, but prediction. Sampling is much simpler after you have learned the Gaussians. Is it okay?
Yes.
So now, my dear, the idea is how can we, so you see there are, say we have, now let us forget about Gaussians for the time being and generalize it a bit. And then we will like maybe go for more like you can think of these as Gaussians, but let us for the time being generalize them. Let us have some notations. Let P of X be the, or rather let me write P of X be the data distribution. Okay. P theta of X is the model distribution. Model distribution of the data. But I tell you, you see from this above Gaussian case that a single Gaussian or a single distribution is not enough to model this. Do you agree? I would have to model it by multiple Gaussians or multiple, a mixture of, this has to be a mixture of similar distributions here. But my question to you is how to decide which Gaussian should be in which mixture, or which data point should belong to which, like which data point should be used to train which Gaussian. Can you tell me that? Once you've just given the data, you cannot visualize it in very, very high dimensional. You cannot directly use any heuristics, right? You need to devise an automated algorithm that will be able to map all these data points to the best Gaussian. Correct?
Like first perform k-means and then
That's a good idea. That's pretty good idea. Perform k-means and
develop a Gaussian for each cluster.
and then mu and sigma. You can try this. This is a very good idea, but this is a very naive idea. Good but naive idea. Had this been so simple, I would not have like. So this is exactly which it will turn out to be. Like at the end of the day, this is a special case. This will be a special case. We'll see. Okay, this will be a special case of what we'll learn. Very nice. You're at least thinking. Good. So this is a good algorithm. You can perform k-means and then fit a Gaussian around it. Okay. So with that, let us see what we can do. Here, what I can do is I can introduce another idea. So you told me perform k-means. What will k-means give me? Good that you are giving me this idea. What will k-means give me? This will give me a cluster ID, right? Cluster ID, right? This is what it will give me. It will help you select the data points in the same cluster and to make, right? So exactly that I'll be doing. So P theta, say P theta of X, right? Is the model distribution. I do not know. So for the time being, do not consider this. If I know the cluster ID, say Z gives me the cluster ID. I can model a distribution, say normal mu I sigma I, right? Say I equal to 1 to k clusters. How many clusters? Yeah, k clusters is what I'm selecting. right? This is what you told me. X given Z.
Yes.
X given Z gives me the cluster. If I know the cluster ID, I can fix this. But I am telling you that I will not use k-means to learn Z. This also I will try to learn somehow. But how? So in this type of algorithm, this is called a latent variable. Latent, what does latent variable mean? What does latent mean? Latent means hidden, right? This variable actually does not belong, is not in the data set, right? In the data set, you may have this height, but this cluster ID is a variable that is very useful to me. It is giving me the distribution from which the height is being sampled, right? So for example, here Z can be equal to 1, Z can be equal to 2, Z can be equal to 3, Z can be equal to 4, right? So this is your latent variable. So now how do you learn this latent variable? Not a very difficult idea to learn. Why? Can you tell me how can I do this? So what is the end goal? Is to learn p theta of x, right? End goal. Or do MLE. That is theta star. End goal is theta star is equal to argmax of theta log of p theta of x, right? Over the data distribution. You have to maximize the probability of the parameters. This is the end goal. But I am saying that only x is not the variables or the random variables. I am introducing one more variable z that will help me to determine which Gaussian is that I'm selecting. Is it clear? So for one data point, let me write log p. Yeah,
Dada, like, can you explain what is that latent variable and what you will do with that?
I have not done anything with it, but is this latent? Is this you told me this algorithm, right? Z is equal to x given is some normal, right? Do you agree? You found out that
Mm-hmm.
using k-means, right?
Yes.
But I am saying that let there be an underlying unknown distribution that is not known. That is the latent or the hidden distribution. That decides. So for example, say you have 4 distributions actually like this. You did not know when data will be given to you, you don't know that which is the latent distribution, right? That is not given to you. You are given only height, right? You have to feed the data now, correct? Is that I'm not going into written models yet. I'm given you all
Okay.
heights. H1,
This
say consider
underlying
delta.
is this underlying distribution which you are telling, that is
Hmm.
like means for height to we know it will be a normal because it is one variable and one dimensional.
Also, multidimensional also it can be normal. I'm not saying that, but height from different countries would be normal in themselves, right? They would not. They
Yes.
cannot be part of the same normal. So uh, the idea is, so H1 to Hn is given to you. Some of them will be in the, say in one country, some in the other. So the latent variable will tell me which country is this in, right? The latent variable will tell me which country and that will help me. So it's like that clustering value, which will tell me which country it is in. And then I will accordingly learn those parameters, right? Clear?
Yes.
Okay. So now you tell me, how do I introduce this latent variable in this maximum likelihood term? in the maximum likelihood term, there is no latent variable. How can I introduce it? And if you want to introduce any random variable to a probability, what do you do?
Do conditional.
Good, conditional. Or you can just do this x comma z, and this is for one data point. I'm not writing this expectation again and again. I'll write it at the end. Okay, I can integrate z out, right? The conditional, whatever you told, same thing, law of total probability. Good. Now your p theta model, your p theta of x is what? This I'll come back to. Let me keep it here. So conditional, let me write p theta of x comma z. What can I write this as? Or whatever I've written, I'm writing it on the left hand side once again. What can I write this as a conditional? P theta of x given z into p theta of z dz, correct? Conditional probability.
Yes.
For discrete case, we'll be considering, because this is going to be discrete only, this will be equal to summation of p theta of x given z is equal to I, probability p theta of z equal to I equal to 1 to k. So if there are k components, right, I want. Do you agree?
Yes.
So now you see I have all these models with me. If I say that p theta of z is some multinomial distribution, multinomial alpha 1, alpha 2, alpha k, and p theta of x given z equal to I is some normal mu I sigma I distribution, right? Just for example, then this is called a GMM. See, this is an average of multiple GMMs, right? Alpha I, this will be alpha I normal x mu I sigma I, right? This is what it will be. It's the average of multiple normal distributions, just like we expected over here. I just assumed these two distributions. These are the two distributions you assume for GMM. You can assume others. In your assignment, you will do exponential, mixture of exponentials. But the basic idea still remains the same. You have to just assume these two distributions accordingly. Gaussians are the best choices, therefore people use GMMs. Clear?
All right. Another one more thing is like
Yeah.
this distribution in particular, I don't know. So will you be using properties of it? Then can you kindly state it?
Which distribution property?
The multinomial.
Multinomial just means normal multinomial, no? Alpha 1 plus alpha 2 dot 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 alpha k equal to 1. Probability of, we have done x is equal to k, or whatever, z is equal to I is equal to alpha I. That's the multinomial. Like binomial,
Acha, acha, acha.
multiple outputs. For example, a die, you have done it in your first assignment, no? A die roll, the probability of 1 by 6, 1 by 6, and so on. That's it.
Yes. Yes.
You're just taking a weighted average of all the normal distributions, right? You're selecting which of the normal distributions you want to take. It's just like k-way classification, like we did it in softmax regression.
Acha, acha. Yes, I remember. Yes.
Okay. So, I'll just also write down the distribution for what is normal for a data point x with mu sigma, mu I sigma I. What is the PDF which I'll be using? Do you remember? This is your distribution. This is the PDF. Okay. So now my question to you is, I could have directly learned this, right? But what is my problem? Why can't I just take derivative of dd theta like this? Can you tell me? If I can do gradient descent, then we write log of summation I equal to 1 to k p theta of, let me not mix the things up here. Why not do theta t plus 1 theta t minus eta dl dt? Can you tell me why? You have to take derivative with respect to what? What are the parameters? Alpha I, mu I, and sigma I, right? Right. If you're asking me what are the
Yes.
parameters, parameters are alpha I, mu I, and sigma I equal to 1 to k. Like, can you do this? Is this differentiable? Is it analytically differentiable? Not analytically. No analytical closed form derivatives. So log of a sum is very difficult to, especially when the parameters are in the logarithm, right? It will become extremely challenging because everything will come to a denominator, and you will have, for every data point, you will have it separate derivative. You can try out any log a plus b and see how difficult it becomes, right? So if you do some log ax plus by and take derivative with respect to a, it becomes ax plus by times x. For y, it will be similar by times that. And similarly, this will continue. For every data point, if you have large number of clusters, taking derivative with respect to the log would be very challenging. And that also when you have exponentials over here, right? These themselves are exponentials, right? They're log sum of exponentials, correct? So there's something like
Yes.
e to the power, the sum of these. Very, very tricky. So this will become something like this. This is very, very notoriously bad it will look like. And you'll have all sort of problems solving them. Therefore, people do not solve them by using gradient descent because there's much better algorithm to solve it, much simpler. It's not these type of algorithm, latent diffusion, latent models, sorry, not diffusion models, latent variable models are not possible to be solved by using these gradient descent directly. You have to find out an intermediate solution where log has to be inside this integral somehow. If it is inside the integral, we'll see it will be useful for us. Because outside the integral, it will not help us at all. It will become very, very difficult. Let's see. So can I write this as p theta of x comma z? So let q be, I'm introducing one distribution. Don't hit your head around it yet. We'll see it how it will be useful. This I am calling as the variational distribution. We'll see why. Don't think too much. It's just yet. It's just a mathematical manipulation I'm doing for the time being. You can think of it that way. Right? This step is, there's nothing wrong in this step. Okay.
Yes. Okay.
So now I write log of, can you tell me what can I write this as? I can write this as log of expected value of p theta of x comma z by q of z comma x, z given x, right? This is my maximum likelihood value, the log likelihood value, correct? I just took lotus distribution, expectation over this distribution, okay?
Acha, acha. Yes, yes.
So f of p of x into f of x is expected value of f of x. That's what I wrote. Now I tell you, ask you this question. So for lotus, I ask you this question. What can I do to bring log inside the integral? That is, bring log inside the expectation. Once I bring the log inside the expectation, my problem will be solved. As soon as I'll get this log somewhere here, right? How to do that? I have, you know, one formula already. We have derived that. I'll draw the picture if you can recall.
Jensen's.
Yes. So in convex functions, what happens? Clearly from the figure, expected value of f of x is always greater than f of expected value of x, correct? Clearly we can see that from the figure. It's above the graph. But then for log is a
Yes.
log is a concave function. So what will it be? So this is log of expected value of x. So this is, the function is f, and this is the expected value. This is your x you can think of, capital A. Then for concave functions, what will happen? F of
Less than
expected
equals.
less than equal to or greater than equal to f of expected value of x. For convex, it is
No,
lesser.
that will be greater than equals to.
Yeah, yeah,
Means this will
yes,
get reversed.
correct, correct. This is concave. Use Jensen. So now you see, have I put the integral? You put the log inside the integral, or put the log inside the summation, whatever you, if you're not, you think it's difficult for integrals, right? I have put it back inside the integral. So therefore, look at this nicely now. Therefore, the p of x log p theta of x is greater than equal to p of x q of z given x log of p theta of x z by q of z given x, right? So this is always lesser, right? Always lesser than the likelihood. Always lesser than or equal to the likelihood, right? Correct. Clearly, we have derived it. This is called the evidence elbow or the evidence lower bound. Let us represent this as f theta of q. Let us stop here for a couple of minutes and try to see what have we done till the time till this time. And I will be happy to answer questions that you have. So I have derived what is an elbow. Now we'll come up with we'll see how to solve the elbow. Why it is useful? Are you getting it now? Now it is simply like solving log likelihood. You will get log of something is just all the expectations are outside. You can approximate them by summations, right? There's no summations inside the log anymore. Here.
Yes.
But then what do I have to do? I have to make if theta q equal to the log, right? I have to put this equality, right? I have to match the equality. I cannot just be somewhere lesser. I have to be equal to the log likelihood. I have to maximize the right hand side, correct?
Yes.
So this is what is done. So we do the elbow has to be maximized. Maximized to maximize the log likelihood. So elbow increases your, that is the right hand side. The left hand side has to increase, right? Because to maintain this inequality, it has to increase. If I'm able to increase the right hand side, I will be automatically increasing the left hand side, correct? So my goal now is to increase the right hand side. I'll be happy to take questions. Any question? After this, will just become calculation. So if you have anything in mind, please get it out of the way.
Can you once repeat what was that QZ given X?
That I'll tell. I have not yet come to it. But other than that, any questions? Is just for the time being, you think of it that is some probability distribution I brought in to bring this expectation so that I could use the Jensen, right? To use Jensen, I brought it in. I will select it accordingly. I will select what it will be. I have not selected it yet. It's a design choice. And therefore, see, I have written the elbow in terms of Q. Q also I have to choose. To solve this problem, I have introduced another optimization problem, that is Q problem. Right? Any other questions? Like mathematically, it is clear, right? What is the objective? I have not yet told.
Yes. And theta would be the mean and the variance. The
Mean,
parameters
variances,
according to
alphas, all the parameters, correct. Q is essentially the distribution of the latents given the data. We'll see how to get that. Anyways. Now, let us consider f theta of q. Right? Let us consider for one data point for the time being. I don't want to write the expectations multiple times. Log. Can I write this way? P theta of z given x, p of x by q of z given x. I can write, which is log p theta of x, right? There's no expectation over x. If I take this out over z, So this
Yes.
is the constant. This is
Yes.
the constant plus expected value of. So let me write it in terms of the integral. It will be easier for you to understand. Q of z given x log of p theta of z given x by q of z given x, right? These two terms here. Do you recall this term? What is this term? We showed this in one of our classes. Yes. Two distributions. We tried to minimize the distance between them when we started with what is how to learn models, what is actually log likelihood. It was actually the KL divergence between the data and the, this is the KL divergence, right? PKL, P and A, Q was P log P by Q dP, whatever. If X was the random variable, right?
Yes.
So the KL divergence was the measure of the distance between the distributions. How far? So whenever they were the nearest, if they were equal, see, this goes to, we showed it, it is always greater than equal to 0. We can also show it now. It is greater than 0. See, if they are equal, this goes to 0. This has to be greater than
Yes.
equal to 0. So now you see, this is the negative of the KL divergence. Do you agree? That Q is in the denominator.
Yes.
So it's the negative of the KL divergence between Q of z given x and p theta of z given x. This we write as f theta of q. Now you tell me something. From this itself, you'll be able to tell me one thing. That is why this also helps you to prove that the KL divergence is greater than 0. Why? See, what is this side is, do you agree this has to be greater than equal to log p theta of x from the very definition? Right, this is log p theta of x, and the right hand side was your f
Yes.
theta of q. Now the writing has not yet appeared. Yeah, the left hand side is log p theta of x. The right hand side is what we calculated just now, p theta of q. Correct.
Yes.
So now you see this also says that KL divergence is greater than 0. This is also another way to show that KL divergence is greater than 0. But we have also shown it independently. So this is greater than 0, we already know, but some circularity is there. You have to prove only once, one of these. Either you have to prove that KL divergence is greater than 0, or you have to start from one of them. Anyways, the idea is log p theta of x is the sum of f theta of q plus the KL divergence, right? Yes or no? Why is it so slow? Yeah, it is here. Just I wrote this on the other side. Clear? I wrote the KL divergence on the left hand side.
Okay.
I just can't. I don't know the. Yeah. Just let me know when this arrow appears. Yeah, I think it has appeared. You understand this? So the log likelihood is this ELBO plus the KL divergence. Do you agree?
Yes.
This is called the free energy. In physics also, In thermodynamics, we've studied this, the Gibbs free energy. And this is what you cannot extract of the, this is what you cannot do anything with the from the system about, and this is what people generally manipulate. Also in machine learning also people try to do that. This is called the free energy, and this is called the, so therefore if you have this as your log p theta of x, you have it in two terms. One is your free energy or your ELBO, and the other term is the KL divergence between q and p theta, right? So there should be a way to, what should be your ideal case? So you are trying to optimize which component? You're trying to optimize f theta of q. You cannot optimize p theta of x, right? P theta of x
Yes.
was, so for that what I have to do? I have to put this to 0, right? I have to make the free energy equal to the total usable energy. The other energy I have to just remove. The ELBO has to be, the KL divergence has to be made to be equal to 0, right? Somehow they should be equal to 0. Then only I'll get p theta equal to fq.
So we were maximizing f theta.
Yes,
Acha, acha. Yes, then okay. Yes.
we try to maximize f theta. There's this, if you consider p theta of x is counts fixed for the time being, we'll see how to increase that as well. This is your f theta, right? This is your free energy. How can you maximize it? It can only be maximized if the KL divergence between q and p theta is become 0. That is minimized.
Yes.
This has to be minimized. So when is that minimized? When is that equal to 0? See, we have a closed form over here.
Like that becomes equal. Both.
That is q of z given x is equal to p theta of, right? Correct? If I can make them equal, then this will go to 0.
Yes.
This is called the expectation step. Now you see, I got the reason for selecting q, right? My q is nothing but the posterior distribution. Right? Posterior distribution of the latent, of the latents. Correct?
Yes.
Now the maximization step. Now you tell me there is this idea that only if I increase, if I change q of z given x, I'm just going to stay here, right? Will I be able to improve this as well? I have to also improve p theta. I have improved, I have made my f theta somewhere here. I have to now improve the bar for log p theta also. And then again, have this handshaking going on to improve both of them somehow. So how can I,
Yes.
how can I improve that? So I can do that. So I will name this as t plus 1, and I will say if t plus theta t plus 1 is arg max of theta, f theta qt plus 1. Whatever maximizes your, this will guarantee that you go up, you make your So f theta now reached here. Now you made your f theta go even further, making the log go up even further, right? Once your f theta went up further, log p theta, the likelihood went up even further. Again, you will try to do the previous step, the expectation step, where you're taking it equal. Why is it called expectation? Because on expectation, the posteriors are being matched, right? The posteriors are being matched to what they're expected to be. And then the name suggests you're maximizing the elbow at every step. So this is called the EM algorithm. This is one static picture to have in mind. The dynamic picture would look something like this. So let us define L theta of t to be log p theta of x. So let this be the L theta that increases. Okay.
All right.
I'd say this is your theta t. This is your L theta t. So now I tell you, what do you see from this picture? From this picture here, L theta t is log of p theta xt, right? So there will be two numbers, right? Two functions. So there will be something. It will be something like this. I'll tell you what does it mean. F theta of q t, right? Or t, yes. This is what it will be, and this is your best theta that you can choose, found by argmax. Yes or no? This is because for all other points here, you will have what? You will have a KL divergence, yes or no?
Acha, acha, acha. The difference is greater than 0.
Correct. Only where there is this KL divergence goes to 0 is your optimal nu theta. Now, once you do that, you will select your QT plus 1 now, right? As soon as you select your QT plus 1, this will become something like this. F theta of QT plus 1. This will become your theta t plus 1. Understood? As soon as you do the expectation, you are bound to follow go to a larger energy state, just like we saw over here, right? This handshaking has to continue. Once you improved f theta, you have extended it to the limit. Now you improved f theta itself, right? By changing your q. Now first change your q, make q theta equal to the log of p theta. Now improve f theta itself so that log of p theta increases even more. Again change the Kn divergence and go on doing it, right? Intuitively it will keep on increasing, right?
Yes.
Is this clear? This is theta, and the y-axis you have L theta, the loss. The objective is to improve the log likelihood. It's not a loss, log likelihood. Okay. So one of the questions that I've asked, so I've derived the expectation maximization algorithm. Now I'm asking you to prove that this algorithm converges. Once we're able to prove that, we'll do a special case and everything will be clear. The GMM is a special case. But this general case is very critical because this gives you a better idea of the things once you look back to it. Okay, the how can I show that? Convergence has to, the objective is to show that. Do you agree? If I can show this, it will show that enough to show convergence. This should
Yes.
suffice. Okay. How do I then show that? So this is called strictly non-decreasing. Okay. What is L theta t? This is f theta of, let me write it down, log t theta tx, right? This is what it is. Correct? Which is equal to what? F theta t q t plus 1 plus dkl qt plus 1. Yes or no? Can I write this? This is equal to 0. The right hand side, I am putting qt plus 1 as the function at in the elbow.
Yes.
This is after, this is how we set it, right? We have set it equal to p theta of p theta t. Please note that there is a t there. This is how we have set it, right? So that it becomes 0. Now, do you agree? This is greater what? F theta t plus 1 qt plus 1. Why? Can you tell me? See, the equation is there on the top in blue. Why it is true? This is there, right? For the time being, even if you forget about this t plus 1, q of t plus 1, what does f theta of q plus f theta t plus 1 mean? How did you get t plus 1 for theta?
Can you
This is
repeat
nothing but
once?
lag.
Your voice is cracking.
From where did it? So I think there's a internet. The weather is bad. See L theta of t is equal to log p theta. This is log p at the tth instant p theta of x, the log likelihood.
Yes.
So that is equal to, we derived, is equal to ELBO plus the tail divergence. Log
Yes.
is the equal to, good. So if I put the value of q to be t plus 1, we have set t plus 1 from the expectation step to be equal to p theta of t. So we get to 0, right? Entire thing, the tail divergence down to 0. That is equal to the elbow.
Acha, yes.
Now I'm telling why is it lesser than f theta t plus 1 of qt plus 1. Why the elbow evaluated at the t plus 1th parameter is always greater than, bound to be greater than the one evaluated at the tth parameter.
Like theta t plus 1 is the theta for which that if theta is maximized theta
Good,
t plus 1.
good. That's what I wanted to know. Maximize it. Maximization step. This is because theta t plus 1 is the argmax of f theta, right? It has to be greatest, right? For the particular qt plus 1 by the definition. Now, that also has to be lesser than equal to what? By elbow? Elbow t plus 1x. This is the elbow equation. No. For any, we have shown this, right? The elbow has to be always less than equal to the log likelihood. Clear? So we showed that L of theta t is equal to L of theta t plus 1. Hence proved. Okay. So before we go into the coding, let's derive the EM algorithm for a mixture of Gaussians. So this is the algorithm. There's nothing more to it. This is the entire idea of latent variables models, be it VAs or anywhere. This is the entire idea that is used. Maybe you will not have a closed form solution like in GMMs, but people use any other approximations there. But the overall overarching idea remains the same. Okay, so let us do it for the GMMs then. For GMM or the Gaussian mixture model. Just derive it. So I'm saying x given z equal to I is distributed as normal or probability whatever. P theta of x z given I is x is the random variable, mu I, sigma I, and zi, the probability of zi is equal to alpha I. Okay? Clear? So for step,
Yes.
what is it going to be? The expectation step, right? Expectation step where you calculate q's, right? Sure. So q we thought was equal to q or the t at t plus 1 instant. Z is equal to I given x. What did we think? Was equal to p theta of, tell me, what did we said in the expectation step? So this is the general case always holds, right? Now we'll do it for the special case. Tell me now, how will I do this? This is the expectation step, no doubt.
This you got from before.
No, yeah, I'll just I'll just keep it written. Theta of q plus dkl of qz given x p theta of. This is the equation I want you to keep in mind. And the second equation I want to keep you in mind is expected value of x, expected value of qz given x, log of p of px comma z by qz given x. Correct? These are the two equations that we generally want. Rest everything is known.
No, no,
Okay.
there was one expectation, na? F theta q.
Yeah, I told them that is for one data point. Now the x is also a
Acha, acha.
list of
Okay.
data points. It's a x is also a data distribution. It has full. I told it was over one data point, so it is over the entire data set. It will be sum of all. Otherwise, this would not have been a random variable. It would have been random variable in x, right? It's a conditional expectation in x. So it would have been dependent on x, which is it not. Okay. So how do I get q of t plus 1? I will have a closed form. Can you tell me how do I get it? I don't know this, but I know something already. I don't know p theta t of whatever z given x. The posterior I don't know, but I know the conditional distributions, right? What should I do? What should I do? Am I audible? For the jth data point, the probability that it belongs to the for j data point, the probability, the variation, the probability that it belongs to cluster I, right? That's what it is. Right hand side I already know, right? Do I know it? Can you hear me?
Yes, yes. You can hear now. Yes.
Yeah, I'm just asking the right hand side, or do I know how do I get the right hand side? Any idea? Can I write this? Bayes rule?
Yes.
The denominator I'm writing because it's a constant, doesn't depend on anything. So now I know all this form, right? Closed form I know. Tell me the closed form. Proportional to alpha I normal xj is the random, xj is the data point, mu I mu j sigma j not j sigma I. Yes or no? It's just the
Acha, acha. Yes, yes. We knew that. Yes.
so now q t plus 1 z equal to I xj is equal to, I'm going to represent this as for the time being for shorthand ij t plus 1, I being the first cluster index, j being the data point index. So you will have k clusters, k cross n as the number of qs. This I'll be getting as alpha I. What do I have to divide to make convert it into a probability?
Divide by summation thing. Summation of that.
Summation of, no, I don't know which summation.
Summation of alpha I normal x.
Okay, alpha I is right. I equal to 1 to k. K. There are k Gaussians. Correct? Good. So now see, I got the Q, right? I have a closed form for Q. Now I'll fix the Q. As I told you before, fix Q ij t plus 1 and update theta. We'll update the theta now. So because just if you're not following, this is summation of Q of ij t plus 1 I equal to 1 to k has to be equal to 1, right? So this is the probability of law of total probability, right? Clear? The data has to belong to one of the data point, right? At the end of the day. Okay. Now the
Yes.
maximization step. In the maximization step, what do? I do theta t plus 1 is equal to argmax of theta, expected value of Ex, expected value of Q of z given x, log of right? I hope I'm audible, right?
Yes.
Okay. So what are my mu thetas here? Alpha I, mu I, sigma I. These are my thetas. Let us try and find it. So I do not know. So this is my f theta of Q. Good. Now I'll have to find out. Write these as a closed form again. So how do I write it as a closed form? Tell me, what will it be? What will I write this as? Argmax theta. Just write theta for the time being. Okay. So argmax over theta. What can I write? Summation over I equal to 1 to n data points for the outer expectation. And for the inner expectation, what can I write? Help me.
Acha. Yes, like that inner part will be qz given x into plus into log of p.
This, right? J equal to 1 to n, or I don't know which one should I write J as, which let me write the first one as I and second one as J. Okay. This is what it is. Expectation over Q.
Like
Oh,
Dada means you are why are not you using Lotus? Because we have that log term inside.
so I have not yet written it. I'm just written the probability term yet.
Acha, acha, okay,
Just
okay. Yes, yes. This will be multiplied by f theta or that one.
yes. I've just not written it yet. I'm just writing the probability. Okay. So now my question to you is, how do I get the values of? So this I already know, right? This is my, again, same thing. This term, t plus 1, z is equal to this, xi, correct?
Acha. Then you can cancel out. Oh no, sorry, log. Yeah, acha, acha, yes.
This is
Yes,
this
yes.
is this is a constant. You are right, but you are wrong in one sense. But this is a constant, right? Doesn't depend on theta. Does it depend on theta? Mu is also not there, sigma is also not there, alpha is also not there. We're going to fix it, right? When we are starting to do maximization step, the variational distribution is fixed. That's how we had seen how they are climbing hand in hand, right? If that is fixed, it's a constant. You have no doubt, right?
Means I couldn't get it.
No, but if anything is fixed, what are you trying to optimize this equation for? Theta, right?
Yes.
So if does q depend on theta, qt plus 1 in the maximization step? It's a constant, it's already given to you. You're not going to change q
No,
in
no, no.
you're not going to change q in the maximization step. You're only going to change theta. Q's are given to you already. They're constants.
Yes.
So whenever I do optimization, constants always are fixed. They don't change my argmax. Do they change the arg magnitude?
No, 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 not at all.
T plus fx. T plus fx. This is fx. Both of them will have the same x star, right? That's what. Okay. Now, this I can write as argmax of theta 1 over n, I equal to 1 to n, j equal to 1 to n, q j I t plus 1 log of p of xj given z is equal to, sorry, xi given z equal to j into probability z equal to j. Correct? Write it down. What are these values again? Argmax over theta 1 over n, I equal to 1 to n, j equal to 1 to k, t plus 1 ji log of, what is alpha j? P of z is equal to alpha j. That is your, this is alpha j, right? Right, this is how we distribute this is how we define the distributions. Okay.
Yes.
And the other one is 1 by 2 pi to the power of, say, d distribution data sigma j to the power half e to the power of minus half x minus xi minus mu j sigma j inverse xi minus mu j. Correct? Okay.
Yes.
But am I really done with it? Is it unconstrained optimization? So now I will be able to solve this and I'll get alpha star, mu star, sigma star, right? Or t plus 1, whatever you want to name them. I'll do it. But first tell me, is it fully unconstrained or is there a constraint that you need to worry about? Any constraints you want to worry about? I'll just go to the definition once again. These are the two definitions. Any constraint? You had asked me this question in the beginning of the class. What is a multinomial? That is the hint.
Acha, summation alpha equals to 1.
Summation of alpha I equal to 1 to n is equal to 1. You can't just take any alpha i's, right? You have to take I equal to 1 to k, not n, sorry, k. 1 to k, alpha equal to 1, right? So and to mu alpha sigma. Tell me what is the Lagrangian?
This full thing.
Okay, let me write down the full thing. So this is the constant, does not depend. So I'm just dropping these constants because dimension of the data still going to be the same for everything. So just drop that constant out. Then we have minus half sigma j, this mod minus half xi minus mu j, sigma j inverse xi minus mu j, right? This is the term you're talking about.
The other like it was a part of the log too.
Log should be there, right?
Uh-huh.
Log, I just forgot to write. The second one log will go because it's an exponential is there, right?
Yes, yes.
So this term is a constant because it is 2 pi to the power that dimensions by 2. Yeah. Okay. Now, question is plus lambda into what? 1 minus
So 1 minus
summation of
summation alpha. Alpha.
good. So now first term, I'll tell you is easy to solve is alpha I. So let us solve the alpha I. So dl d alpha I, what will it be? Because the Lagrangian multiplier is what we have to remove first, right? Lagrange multipliers. Therefore, I'm going to solve that first. So tell me what is going to be the derivative? I equal to 1 over n q of ji, right?
Yes. Or like that will be 1 by alpha j only. Yes.
Alpha j minus alpha, correct? Not alpha j, alpha I. Wait.
Uh-huh.
Derivative I have taken. No. I should let me write j on the left hand side. It will be easier, right? Because I will
Yes.
be mixed up with j if I don't write that. Because I is the number of data points, right? It's going over the data points. Okay. So now what will I get? I'll get alpha into lambda j. Lambda into alpha j is equal to 1 by n summation of I equal to 1 to n q j I t plus 1. Correct? Here.
Yes.
But again, I can lambda, the Lagrange multipliers have not been removed. How can I remove it? Tell me, very easy. What should I do to remove the lambda? Very intelligent trick you can use.
Acha, sir, put a summation.
Good. J equal to 1 to k. If I put a summation over 1 to k, this summation becomes equal to 1 into lambda. The right hand side becomes I equal to 1 to n 1 over n summation of I equal to 1 to k q of ji t plus 1. So what is this value? Summation of qz equal to j given xi, j equal to 1 to k. What is this value? Over k clusters
Acha, 1.
or k? 1. Law of total probability. So this is equal to 1. So 1 into n, lambda becomes equal to 1, right? Clear?
There you interchange the summation, right?
Yeah. What is the problem? There's no issue, right?
Acha, acha, yes.
Okay. So from here I get this equation that alpha j. So I have got one equation, right? Okay, so to let me write these equations in a good, nice form. So I think the E step is written well. The M step, I will write it. Where should I write it? Wait. I'll just try copy this to the bit to the end. Okay. And I will write this. So the first equation, the M steps, I got alpha t plus 1 j as 1 by n summation of I equal to 1 to n qji t plus 1, right? This is what I got. E step, what did I get? Having everything together. This was equal to alpha j, correct. Alpha j normal xi mu j sigma j summation of j equal to 1 to k alpha j normal xi mu j sigma j. Clear? These are the two equations I have got till now. Okay. Next, what will I find? dl d mu j. Tell me what will dl d mu j be? Look at this equation. Is my internet connection okay?
Yes.
So I did take the derivative with respect to mu j. I get what? I get 1
Like
over n.
that summation.
Yes, I get. So we have seen in previous classes that Q transpose SU du is for a symmetric matrix. It is 2 SU, correct? We have derived it quite a few times.
Yes.
So now you see I'll get I equal to 1 to n. Again, j goes away because I'm taking the derivative with respect to j. So I'll get what? Minus 1 by n sigma j inverse xi minus mu j, correct? This has to be equal to 0. Which is?
Yes.
So sigma j has to be invertible. We have already shown that. So I multiply sigma j on both sides. So I get, remove this as well. So I get, what do I get? Sorry, I forgot to write qjit plus 1. That is also there as a constant multiplying. So I equal to 1 to n I equal to 1 to n qji t plus 1 xi divided by, let me write it fair and square, I equal to 1 to n qji, right? This is what it is. This equation on the top.
Like, why did you remove 1 by n?
It's a constant 1 by n equal to 0, na?
Acha, 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 yes, yes, equals to 0, yes.
Multiplication constant equal to 0. I'm putting it to 0 because I want to take the extrema or whatever is minimizing it, or maximizing the elbow. So what is this value?
Yes,
This summation of j equal to 1 to n.
again 1.
This will give me an idea. I think you can tell me. See, from this equation, you can be able to tell me 1 by n summation of I equal to 1 to n qji. Already I have written this. Why am I writing it again? So this equation will give me the value, right? Correct. This summation of q is on the right hand side of this equation.
Yes.
Your voice is breaking. Can you tell me once?
Yes, yes.
This will become n into alpha j. So 1 by n into alpha j t plus 1 I equal to 1 to n q ji t plus 1 xi is equal to mu j. So let me write mu j t plus 1 as 1 by n alpha j t plus 1 summation of I equal to 1 to n qji t plus 1 xi. Now tell me, does this look very familiar? This is what? This is a weighted sample mean, right? Yes or no? This is like calculating total mass in jth class. Right? If you worst case, they would have all been ones, you would tell that number of data points or something like that. Isn't it? This is nothing but the weighted average of the clusters of the data points, all data points, right? If you did not have these queues, you would have only summation of xi's, then that was nothing but the average of the data, right?
Acha, acha, summation al qji, that is 1. So, like, putting weights
So
wi.
yes, exactly. Now this let us find the final one. dl d sigma j equal to 1 to n. Let's let third term. Let's not putting n here. J equal to 1 to k, and I'm just keeping the half log sigma j plus, both are minus, so I'm keeping only plus. This is equal to 0. X minus mu j sigma I inverse xi minus mu j. So now I have to take the derivative with respect to sigma j, right? This matrix. For this, you need a little bit of more calculations, just a lot of hand keeping. bookkeeping and everything. So to avoid that, I have brought in the formula from this Wikipedia page. You can refer to that. It's very useful for taking derivatives with respect to matrices and vectors. So you can, these are very standard formula, but to derive them will take some time because they're matrices at the end of the day. And it'll be some algebra to do. So I'll not do that, to do something more interesting. Okay. So tell me what is that? I'll just use this formula directly. So this term will become, so half also I'm just removing. Both are half. So so what this term will become? Tell me, only j, you're taking respect to j only, the jth what is covariance matrix. So this is going to be 1 by sigma j inverse, right? But the second term, how am I going to use this formula, this trace formula? Any idea? Yeah, any idea? So U transpose SU, can we write this as trace of U transpose SU? And yes, if it is yes, then tell me why. So first of all, this is a scalar, right? This is 1 cross n, this is n cross n, this is n cross 1. So this is the quadratic that we saw was equal to is a scalar. So if it is a scalar, then if it is a scalar, hello, trace of a scalar is itself.
Yes.
So we have shown the trace of AB. This was one of the identities that I showed, is equal to trace of BA. Very well known identity, and we have also shown it. This is nothing but equal to trace of U transpose S, which is also equal to trace of S U transpose. Same thing. Correct. So I can write this as
No, like
trace of,
you are calculating trace of a scalar.
yes, trace of a scalar is equal to the scalar only, na?
Yes.
But then I can, since these are vectors inside, I can do that on this property. I can use trace of AB equal to trace of BA that I showed before.
Acha,
And
yes.
now these are matrices. So sigma j inverse xi minus mu j, xi minus mu j transpose. Okay, the derivative of this with respect to sigma j. This we have seen as twice, write the inverse on both sides. Sigma j inverse xi minus mu j, xi minus mu j transpose sigma j inverse with a negative sign. This gets cancelled. Sigma j inverse, right? Sorry again, I forgot to put in the q's. Qjit plus 1. Please be careful with respect to the q's. Q's are very important over here. Qjit plus 1, because they are the ones that give you the weights for the weighted sums. Okay, this is the I equal to 1 to n. This is equal to 0. I equal to 1 to n qji t plus 1. Clear?
Yes.
Now I can write this as sigma j inverse summation of I equal to 1 to n q j I t plus 1. This I already know. I'll keep it to my handy. This is going to be q j I t plus 1 xi minus mu j xi minus mu j transpose I equal to 1 to n. Right? Clear? Okay, now I multiply
Galvez,
since this is.
what did you do to? Acha, acha, okay.
I didn't do anything. It's just lag. So I'll just put on both sides sigma j, right? This is what I can do, right?
Acha, yes, yes.
This will become I, this will become I, this will become I. So sigma j will become, this already I know, lambda alpha j t plus 1, right?
Yes.
So 1 by lambda alpha j t plus 1 is equal to this 1 plus n q j I t plus 1 xi minus mu j t plus 1 xi minus mu j t plus 1. So see, it's again the weighted covariance matrix, right? Same thing. It's the mu and sigma is the same as you would calculate in case of a normal Gaussian, right? But which one you need to choose? That is told by Q. Q is telling you which is near to which data point. Sort of will tell which is more probable to be in that underlying distribution, right? That's the latent distribution that we had seen in the beginning, right?
Yes.
So this completes your algorithm. So this gives you how to weigh the means and variance. Variance based on important points. So to conclude, before I go into the code of EM, I'll show you how to implement it. I'll conclude today by giving you a overall story. That is, I'll show you that k-means is nothing but a special case of GMM algorithm. This is the last theoretical thing for this course. Can you tell me how can we show that? So this is why I told you the k-means, k-means algorithm is bound to converge. I told you I'll do it when I do it in GMM. Correct? Isn't it? So the k-means is a special case of the GMM algorithm. So if you take the sigma j's to be a constant, k into identity matrix, very close. These k's are very close to 0 and everything else is 0. Then you will get a k-means algorithm. So in the expectation step, what will happen? Right? Okay, you have these k mu's. So let us write it down. Qj I t plus 1 is alpha j exponential value of x minus xi minus mu j. Since it's a diagonal matrix, this is what I'll get, right? Yes or no? Do you agree?
Acha, yes.
By summation of alpha j e to the power of xi minus mu j square. So now all these terms, this is close to 0. So it is e to the power minus infinity close to 0, right? Yes or no? All these terms are close to
Uh-huh.
0. So I have to select the largest term. Say xi minus mu j, right, is less than xi minus mu k for all k not equal to j. What will happen? Can I write this as alpha j by alpha j plus summation k not equal to j e to the power of minus xi minus mu k squared minus xi minus mu j squared by 2k. Can I write?
Acha, you divided. All right.
Yes, I just divided by the, so this is mu ji. If j, if jth cluster, so let me draw all the clusters.
Can you
See,
change the
huh?
index for that? Say you have written mu j and mu k. That please change that index k, because k you have already used now.
K I have used where? Oh, sorry. What should I use? Tell. L.
Yes.
L is okay, na? L not is equal to j. Thank you. This is a good observation. Okay. So cluster one,
Yes.
one data point, you see that it is closest to cluster 3. Only the point that is closest to whichever cluster, I'm going to select that. So by design, this term will become, this is always greater than 0, this internal term. So e to the power negative by 0 is e to the power minus negative infinity. This summation goes to 0, right? Correct. For all those other terms.
Yes.
So this is equal to 1 if what? If mu j is the, or cj, what should I write? Tell me. Xi is closest to mu j, right? 0 otherwise. Right? Otherwise, you can see it is clearly 0 because this term will become greater than 0. Greater than, at least like it will become infinity. Yes or no? Because for other terms, there will be one term at least that will be negative. Yes or no? This exponent term will become positive for at least one of them if it is not the minimum. Correct?
Acha. So then minus gets cancelled. So it
Yes.
becomes e power plus in positive infinity.
Plus infinity it will become. So like the expectation step, this is why I told you in the GMM or the k-means algorithm that expectation step is selecting the closest means, right? This is exactly what is being done. Selecting the closest mean to each data point.
Acha. Yes.
And in the maximization step, what is being done? See, mu j is 1 by n alpha j t plus 1 uji t plus 1 xi I equal to 1 to n. First tell me what is alpha j t plus 1. This is equal to 1 by n uj I t plus 1 I equal to 1 to n, right?
Acha, it will become 1 by n then.
Not 1 by n. This will be
Sorry.
number of points in cluster j by n, right? This is all either 1 or 0, the numerator. Some points will be in cluster was some more than one also can be in cluster in a single cluster, right?
Acha, for the jth cluster, in the jth
Yes,
cluster, how many points are there?
number of points in the jth cluster. And similarly, see this only, so this is like an indicator function now. This is becoming the average of x belongs to the jth cluster, right? Correct?
Yes.
So this becomes the k-means. So this is why all the nice properties holds because of the GMM algorithm. So whatever you told was also a correct algorithm, but it's a special case. Just now, like I told you. So let us see, like if you don't have any theoretical questions, I'll go to the implementations. I'll wait for a minute. I have covered more or less everything. And a little bit much more than that. I hope this gives you some motivation and some help. Today's implementation also will be very interesting. So any questions you have? Submit your
No,
assignment.
it's fine.
Yeah.
No, it's fine.
Yeah, I think I was disconnected for a while. Yeah, I'll wait till the 15th of June and then I'll start correcting the assignments because people also get a certificate when they complete these courses. These are all not unofficial, they're value added courses in the department. So they'll generally be credited and like useful certificates for you to have. Okay, I'll share the screen now. I'll have the equations on the left hand side. Let me know when you can see my screen. You can see my screen, right?
Yes.
Let the equation just come up. I've written it down in some separately. Na? It'll come up in a while. Okay. Here you go. So these are the equations. I'll just breeze you through them. You can see the equations on the left and the screens on my right, right?
Yes.
And the code on. Okay. So here I'm going to use numpy for your assignment extensively. Import it as well. This is the MNIST dataset. I have tried using some little advanced dataset this time. So this dataset has 784 features. So this is loading. So there'll be 70,000 data points with each 28 by 28 being in their shape. I don't know why it is taking so long. What 404? Is there an internet issue? Yeah, it has loaded. So this is the MNIST dataset I'm loading, and this is what I'm visualizing. So this is what is the handwritten digits as. So everything is written in hand, and you'll be using this extensively in your two assignments, supervised and unsupervised. You can see that the digits. If you can hear me, please respond. I can't see you now.
Yes, I can hear you.
Okay. Now my screen is gone. Yeah. Okay. So now you see what I've done is I have subsampled them 10,000 of them. So this also is one of your assignment 4 questions. Subsample 10,000 of them with 1,000 per class, like 1,000 tens, 1,000 zeros, 1,000 ones, and so on. So at the end of the day, I have 10,000 into 784 features, right? This is my training. This is my data. That is 10,000 data points with 784 features. And these are the corresponding labels. So there'll be, if I show you the labels, what are the labels that I have? 10K. You'll see it's between 0 and 10. So each of them I have manually selected to be 10,000 of them. So principal component analysis is one of your assignment questions. So I have not coded it myself. I have used a library so that you do not copy. So what I do is to visualize the data set, I am converting the data set into 2 dimensions from 784 dimensions. So I do principal component analysis that we did in the last class. We take the first 2 directions of maximum variance, convert the 10,000 cross 784 to 10,000 cross 2-dimensional space. Now I plot this in a 2D space. Now you see so nicely the zeros are in one side, the ones are here, twos are somewhere here, the nines are here, sixes are here, sevens are here, and so on, right? So they're sort of capturing the features, right? Even in the 2D space. This is what I was telling in PCA, that they generally capture most of the variance, right? Can you see?
Yes.
So the ones are clustered here. This
You
is
are
very
very
interesting to
distinct.
see. Yeah.
Few are very distinct, but some have got
Yeah,
mixed.
they have, like, for example, 2 and 3 will have very similar features. You can see they have similar features. I think they are capturing the top of the 2 there. If you take more components, they may be separated out. Right? Like, but more components is difficult to visualize. Like think now in if you have something in 3D, something that is separated in the Z axis, but say have same X and Y axis, but you're seeing it in the XY plane, you'll see them together. I know.
That cannot be plotted here in Python. 3D.
Yeah, it can be plotted. You can plot. In your assignment, you can try 3D. You may have little more separation. Actually, you need much like 10, 15 dimensions. But anyways, but in 2D only, you can see the clusters very well. Like 7 and 9 are being clustered. Like 0 is being clustered. 1 is being clustered. And this is now without using any labels. Labels are used post hoc to give the colors to these points, right? You can plot 3D using the same functions.
Achha.
Try it out, you'll enjoy it. So in GMM, what is I'm doing? I am taking the data. I'm taking the number of mixtures I want. That is, I'm fixing K. Data is some n cross d dimensions. Q is the variational distribution that I have. Mu's I have not yet set. Alphas not yet set. Sigmas not yet set. So first, when I get the object, I initialize these parameters. I initialize them by setting the sigmas to the covariance of the data. I set them equal to the covariance of the data. And for the means, what do I do? For the means, where do I select? Yeah. initialize parameters. For the means, what do? I sample it from a normal distribution of the entire of the features of each feature for its mean and standard deviation. For each feature, its mean and standard deviation, I use it to sample the mean of the clusters. So these are the starting points of the mean and standard deviation, so that because it's an iterative algorithm, you need to have a starting point. So I initialize this data in this form. So where you take the means from the for each feature as the mean of, say you have two features right here. So I take the say the first feature is some between 0 -2 to, so the first feature is between -2 to 6. So I will sample. So the first feature's average is something around 1. So I will sample between -1 and 1. So if two clusters are here, 1 and point here, 1 point here, I'll sample. Similarly, along y-axis also, I'll sample along this mean and standard deviation. So I'll use both of them to sample points randomly along this cluster. Is it clear? That's what I'm doing. For sigmas, I'm setting it equal to the data sigma. Alphas, I'm putting it to be equal probability. And Q also, I'm putting it to be equal probability. Is it clear? Is the starting criteria clear? Only the means I
Acha.
initialize intelligently.
Like
Yeah.
Q will remain constant. So like you have put Q, money Q will not get updated. So
You will get updated
or
in
Q will,
expectation step, na? Qt plus 1 every time will be updated.
acha, in that step with P. Yes.
You will
Okay.
do it alternatively, na? First expectation, then maximization. Expectation maximization, just like k-means. So get, because that's how you're going to increase one after the other, one above the other. Then this is what is calculating the normal value. So value of the normal. So see. So for each data point, I'm just taking the so this is the coefficient 1 by 2 to the power d by 2 sigma to the power half and e to the power of x minus mu. So you can see this is x jth data point and ith cluster minus the inverse of the ith data point and the x minus mu transpose. So this is the, it will give you all the probabilities, all the distances from the data. Similarly, from the expectation step, I will get the all the normal distribution values and I will just divide by the sum, correct or wrong. Right? This is what I'm doing. This get all normal values will give me these normals in xi mu sigma, right? This function is giving me xi mu sigma. So you can see calculate easily. So mu sigma is the inverse of the sigma. This is the determinant, and then this is the PDF, right? You can see.
Yes.
So this will give me all the mu values in the expectation step. What am I going to do? I'm just going to divide by the sum of. So I'm dividing by the sum of all the. So first dimension here is the dimension across all the mixtures. So I'm dividing by the sum of that. So I'm going to get all the QIs. In the maximization step, what do I do? In the self.alphas, again, self.alphas, I take the mean, right? This is the mean, nothing but the mean across all the data points, correct? Of the Qs, see, self.q. Yes or no? Sum of across all the data points, this is nothing but the mean across the data points, right? So here Q is a, if you want to really know it, it's a n cross k dimensional matrix. So n data points, k vectors. So it will take the average across the n. So it will give you k numbers, right? K alphas. Okay.
Acha. Yes.
So now your norm term, whatever norm you're seeing over here, this is going to be helping you to normalize this denominator over here. So this is, you see, q j I x I. I equal to 1 to n. Does it look familiar to something? It looks familiar to a vector matrix product, right? So if I, so Q again, recall the Q dimension is n cross k. X dimension is n cross d. So if I do Q transpose X, will I get k cross d? I'll get all the outputs, right? In this form.
Yes.
So that's what I did. I put all the mu's in a vectorized form instead of writing a for loop. But what for loop I cannot write, I have to write a tensor equation for that. I'm not going to do that. I don't know that well. So I'll write a for loop for that is the covariance part. The covariance part, I will have to write x minus x tilde and so on. I'm going to write it for each of these j's from 1 to n. See, I have done that, x minus mu. See, instead of putting the q separately, I have put it in 1 x tilde square root, and then I have gone put in x transpose x. That will do, right? Just consider x tilde's dimension. So this will be also become k cross k. So then in the EM step, say you want to run 100 epochs. So I'll do expectation step and maximization step alternatively. Now here you can do many things. You can try playing at home with trying to visualize the Gaussians, try to sample from them, all these things you can do, and try to maybe take a inverse transform. You can do many things. I can give you a nice homework. Do something like that. Let us complete and then you can do it. So then what I'm doing here is I am taking a return clustering value. So what clustering is happening here is this is actually giving you the maximum probability like we did in k-means, right? So this is helping you to see the posterior distribution, sort of trying to let you infer the distributions. Let us see. So I'm going to use 10 components now, 10 mixtures of the Gaussian. I'm going to run it. Take some time. So the slower algorithm. So in that time, I can tell you the homework. So what you're going to try to do is, now you know the 10 components, right? You know the mu, sigmas, and so on. Try to sample from the data points. For example, you have this 10 components. You sample from this multinomial 10, you will get one Gaussian. So say your mu i's are 0.2, 0.5, 0.6, 0.8, 0.1. You sampled and say you got the jth cluster. Now jth cluster has its own mu and sigma. Try to sample from that. And then you will get the PC dimensions of both x and y. Try to do the inverse transform with the PC and see if you have been able to generate a new data point. Are you following? Like maybe I'll write it down once this computes, and then you will be able to follow. Very nice idea. We can try it out. You can also try sampling. You can try draw the distributions and so on. It's taking a bit of a time because it's 10 components. Okay, let it run. Okay. While it runs, let me just write it down over here. Do you understand my question that I have?
Now, means the first part I couldn't understand. Means
So,
after getting the mu sigma of cluster, then I will use invert,
yes,
get the distribution, and then inverse transform to get points from it. So
yes. So
what was the first part?
first you can use the to give a point, right? So now if I give you a new point, you can tell me which is close to which cluster. That you can tell me, yes or no?
Yes.
By seeing which has maximum probability. By seeing p theta of the normal distribution value, right? Because the normal distribution of mu sigma will give me a number, right? Whichever is maximum it will belong to that data point, right? Will belong to that cluster. This is the way you can use it for clustering, correct?
Yes.
For a new data point, you will see which normal distributions have maximum normal, which has maximum PDF. But for sampling, what you will do? So you have multinomial mu1, mu2, dot dot dot. Let me run the other. So Look at this. See, clearly clusters the thing into 10 parts. You are saying, see, everything has been nicely clustered. There's no mixing, right? So here you may ask me,
Like,
Dada, but where
so
is the
it is
digit
better
information?
than PCA.
Yeah, yeah.
It is better than PCA then. It's
No, but
much better.
I am training it on PCA, right? It's not just clusters. The data is the PCA data. I am just running GMM on the PCA data, two-dimensional data. So
Acha, acha, acha.
each of them may not be 0, 1. This may not be 0. This may not be 1. This is actually 1 we have seen. This is 1. This is 0. But these are different clusters. This is your unsupervised learning, right? So you don't know which is which label, but you know that they are tightly clustered. See? Similarly, let 5 components run. And similarly, you can see. So mu1 to mu k, you can sample, right? Say you put a die roll, you put a dice roll, and out of the 6, you select some k, right? Whatever, say, or you roll a dice and see whichever has head comes up. Say maybe mu k comes up. The kth distribution, kth point comes up. Kth output comes up. Outcome. Then you sample from sample x given z equal to k. So step 1, sample z. Step 2, sample x given z equal to k, right? Now it is in the PC space. So once you are able to sample x, you can take the inverse PCA and see if you are able to see any picture in the original MNIST space. Up to this first 2 is the EM part, and the second thing is just to see the experimentation and the implementation part. To see now with 5 clusters also you have nice clustering. So EM gives you these long, but does not force you to make circular clusters. It can be give you any type of clustering which it feels is will be the best for you to minimize the ELBO or maximize the ELBO. Is this clear? What I said in this. So since X is in 2D space, I used this PCA to convert it into 2D space. I can sample it from a 2D space and then do an inverse transform to get this into this digit space. And then I can plot the digits and see if actually I'm able to generate some digits or not. Those digits nobody will be writing. You will only generate, right? That's why it's called a generative model. Clear? Any questions? If not, I'll stop because this is the last session. Any questions?
No, Dada.
Okay, so if no more questions, maybe if you all want some doubt clearance after I share the solutions to the assignments, you may ask me. I'll be happy to help. But with that, we come course, which we covered most of the GATE syllabus and also beyond for many of its applications of machine learning, AI, and mathematics related to that. Hope it helped. See you around. Need any help, please ask in the group. Once you submit the assignments, I'll check it and return them back to you. I'll share the solutions also. And 15th June is the deadline for all the assignments. Okay. I'll stop recording if there's no more questions. Please feel free share. Please share this if you can, because the code I have already shared with you. You can just change code parts here and there, and then you can share it if you want. Thanks. So I'll stop sharing, stop recording. Okay.